Okay, so in an effort to help students in class this semester, I'm going to go ahead and make recordings of myself going over worksheets that I presented to classes over this past year. Of course, this past year has been a strange one in education because we've had the COVID pandemic that has prevented us from meeting face-to-face. And so even in my face-to-face, what would typically be my face-to-face environment, I haven't been able to get a full allotment of students into the classroom. So what I've been doing is presenting lots of material virtually, but then bringing small sections of students into the class to do worksheets on the recordings that you in the fully online environment over this semester are, of course, listening to. And I got a lot of feedback on those worksheets that students find them very helpful in connecting the dots and getting through the material that they need to get through. So I want to go ahead and present you with the opportunity to look at those worksheets, to practice using those worksheets, and then to get some feedback with those worksheets in the hopes that they will help you just as they've benefited students in previous semesters. So that's the idea here. And so what we're doing now is our first worksheet that I released to you. And the idea would be that you would go ahead and do the worksheet on your own time, and then you would come back after doing that and you would listen to this recording and get that feedback that I think is really crucial to see if you're on the right track with things. Okay, I decided to go ahead and do this asynchronously because in the fully online or virtual session, I know that many of you are non-traditional students or you have jobs that prevent you from meeting in a synchronous environment on a regular basis. So I'm going to be committed to remaining asynchronous in this and just giving you these recordings rather than bringing the whole class together to do these worksheets. Okay. All right, so let's look at this first worksheet. And the first worksheet is really an overview of Chapter 1. So Chapters 1, 2, and 3 of the class are reviews of the material that are going to set the foundation for biochemistry. So Chapter 1 in particular, we're looking at the physical foundations for biochemistry. And when we think about a biological organism, we can kind of think about it crudely as being comprised of just parts, and those then parts can then participate in these processes that carry out the functions that need to be in place for something to be considered living, like reproduction and that kind of stuff, right? Metabolism, all these types of things. But there has to be something that drives those particular processes in the direction that we see them go, okay? And that would be the driving forces, and the driving forces really are thermodynamics, okay? We can describe the driving forces, by a close analysis of thermodynamics. So let's just go ahead and look here at what would have been the first activity in this worksheet, and read it. It says, so I worked out this morning. Did you? In fact, I did a body combat training video by Les Mills in which I boxed, kicked, ran, jumped, crunched, and pushed my body into shape. At the end of it, I was dripping in sweat and breathing hard. In every move I did, the first two laws of thermodynamics were in full force. So here's what I want you to do. For a single jump, I want you to outline the transfer of energy starting at a glucose molecule in a muscle cell to the pinnacle of my jump. Okay, and then it's true, I was only 36 inches off the ground if you read that. I was pretty tired this morning. So, but anyway, the outline should be at the minimum state the form of energy we see exchanged in each step. By this I mean that you need to trace where the energy came from to start that step and where it ended after each of those steps. Right, so let's go ahead and look at this. Now, no doubt your worksheet's going to look very different, and how you trace this out is going to look very different from mine, but that's okay. Hopefully you get the general concept here. And in this first and second law of thermodynamics, we're looking at how energy can't, first of all, be created and destroyed, but it can be transferred from a system to the surroundings, okay? And it's those energy transfers that we really care about and that are really driving certain processes in certain directions, okay? And so we just simply want to recognize, well, okay, what are the energy transfers that are required for you and I to do something like run or to walk or to jump or something along those lines? What needs to take place from an energetic standpoint to allow that to occur? What's the driving force for it, if you will? Okay, so let's go ahead and do this, and hopefully one of the things that you ask yourself as you consider, well, what does my cell need to jump, right? In other words, what does my cell need to allow for it to contract, a muscle cell to contract? And certainly energy is needed, okay, but in what form is that energy? And hopefully what's coming to your mind as you think about that is the molecule ATP. Okay, so ATP is a very important molecule. We'll be talking a lot about ATP in the future of this class, in particular related to metabolism, but your cell needs at a minimum ATP to allow for contraction, and this would be a muscle cell that we're thinking about. Okay, so the next question you have to ask yourself is, okay, well, is there enough ATP within our cells to allow for a 30-minute workout or a 40-minute workout? And hopefully your next answer would be, no, there's not enough. That's why we do work out, so we can burn what we commonly say burn calories. We burn calories to make that ATP so that we can continue to contract our muscle. Okay, so no, there's not enough ATP in your muscle cell. In fact, there is probably a second's worth, maybe less, of ATP in your muscle cell to allow for contraction. Okay. Other than that, then it has to be regenerated. It has to be made. Okay, so we'll start here. Okay, and I'm going to do this. We'll start with the nutrient glucose in our diagram. So glucose, a 6-carbon molecule, we'll be looking at closely in metabolism, but it can be broken down into carbon dioxide and water. Okay, I'm not going to get too hung up here on stoichiometry. Okay, but you would have to have oxygen to do this. Okay, and so that would be then some process. Now, when we think about this, the molecule here, glucose, okay, this would be a chemical form of energy. It has a chemical potential to it. Okay, and so that's the form of energy that it has. Now, of course, we're not going to get into this in this class, but we could go through the processes of photosynthesis and ultimately trace this back to the sun and the nuclear energy within the sun that then transfers this energy into the plant. The plant then uses it to make glucose, right? And then, of course, we consume the plant, or another animal that has consumed the plant, and that's where we get our energy from. All right, now, as this thing proceeds, okay, and we'll be thinking about this later on in the class, but this is going to then make that ATP. Okay, energy is going to be transferred from glucose, it's got its energy from the sun, into this molecule ATP, and then ATP can undergo another reaction, and that is going to be then the conversion of ATP to ADP and something called inorganic phosphate. Okay, once again, this molecule here represents a chemical form of energy. Okay, and energy is going to, of course, come out of ATP as it does this. Okay, and that energy is going to be harnessed by proteins, particular proteins within our muscle cells that are going to undergo changes in shape, what we call conformational changes. So I'll just say a protein conformational change happens here. As a result of ATP contraction, or I'm sorry, ATP, what we call hydrolysis. Okay, not contraction, I got ahead of myself. Okay, right, so that's then going to be a different type of energy, right? Now we're having a protein that was in one shape prior to ATP hydrolysis, and then another shape after ATP hydrolysis. It's more complicated than that, but we're not going to get into it. If you've studied muscle contraction on a molecular basis, you know a little bit more about what I'm talking about here. Okay, but I don't want to get into the nitty-gritties of this, but I do want to say that this is a mechanical form of energy once we get to this place, because now we have things changing, moving now. Okay. Now, again, we get into lots of, kinesiology and biokinetics and that kind of thing, but we don't want to do that in this class. We just want to say that protein conformational change will cause muscle contraction, right? And once again, that's a mechanical form of energy. And then that muscle contraction is going to lead to the jump. Okay, which is essentially a mechanical, or some of you might have put something like kinetic form of energy. Okay, so I could even say this is a kinetic form of energy. And honestly, we could probably say that the other two, protein conformational change and contraction, are kinetic forms of energy as well. Okay, now at the pinnacle of the jump, right, all of a sudden you reach the pinnacle of your jump, 36 inches off the ground for me. Okay, and all that energy now, if we were to take a snapshot and freeze you there, would be stored as potential energy. Okay, that has the gravitational pull of the earth going to pull it back down into the earth to convert it back to kinetic energy. Right, to get all that potential energy, we've started all the way up here with that chemical form of energy of glucose. Okay, so much of the energy from glucose is now stored in your body, which has a certain position above the ground that would be potential energy. Okay, now all that's great. So that is the first law of thermodynamics. As you look at this, we've got energies being being conserved from glucose all the way into potential energy of your position above the ground at the end of your jump. Okay, right now, we haven't yet really thought about the second law of thermodynamics. Okay, in fact, it says this. Once you've made your outline on this, I'm reading from the worksheet, I want you to now go back and discuss whether you've illustrated the second law of thermodynamics in your outline, and we haven't yet. Okay, so what we need to do is say this. We need to put at each of these places, we're not going to be 100% efficient. And in most instances, we're going to lose some energy as heat. Okay, and once I do that, now I've taken into account the fact that there is a second law of thermodynamics. Okay, that all that energy, those useful forms of energy are being degraded to less useful forms of energy until finally they're, been given totally, holistically over to entropy. Okay. And so that's what we see here, is that heat is being removed from our system as a form of heat that isn't being used to do work. Okay? Right now, that really leads us into the next portion of this, right? So as we consider these useful transfers of energy, we can consider, for instance, in glucose, that there's a certain amount of free energy in glucose. And free energy is the amount of energy, the proportion of the portion of the total energy in the cell or in a system that can do work. Okay, so it's the useful forms of energy. Okay, and as we see chemical conversions, or we see conversions of energy, we're using some of that useful energy, the free energy, to do work, such as make ATP or cause protein conformational changes or cause contraction. But then we're seeing some of that energy lost. It's not useful forms of energy, and that's the second law of thermodynamics. Okay, now that brings us to our next portion of the worksheet. So let me go here. Okay, we'll go to the next blank sheet. Okay, and let's read through this. Activity number 2. Now, again, you want to pause and you want to think to yourself, okay, well, I'm going to do this, and then I'm going to get his feedback. And in particular, in these free energy landscapes, students typically need some help with this. Okay, so it says this, no doubt we discussed ATP for relaxed activity. ATP has to be both made and broken down in the cell as such. Okay, so I have ATP hydrolysis in one instance, and then ATP production in another instance. It gives us these delta G values. So here comes the fun part. I want you to construct an accurate free energy landscape for each of these conditions, for each of these reactions. Okay, please make sure you label KEQ and your initial conditions, and the starting initial conditions for both the standard and actual free energy. Okay. All right, so let's go ahead and look at this, and let's just do the ATP hydrolysis one, okay? And so we'll write out here that you have ATP, and we'll include water in this, okay? And that's going to make ADP, an inorganic phosphate, okay? Now, there's two numbers that are given to us. There's a delta G prime naught, and in this case is negative 30.5 kilojoules per mole per volt. I'm sorry, not per volt. That's another thing. I'm sorry, got ahead of myself. But it is negative 30.5 kilojoules per mole, and then our delta G of a reaction is going to be, interestingly, negative 52 kilojoules. Okay, and this would be our actual free energy change. Okay, and so what we want to do is take a little bit of time and think about, okay, we've got these two values. What can we use these, or how can we use these values to make these free energy landscapes, and what do these free energy landscapes tell us about these values? Okay, and so the first thing that we want to do is look at this. Okay, and the standard free energy change, we have to first of all understand that this is kind of like sea level is to a measurement of altitude. Okay, and by that we mean that with sea level, that's our standard, that's our reference point, that's how we measure altitude. Okay, and so when we think about free energy changes, we want to have some sea level. Okay, in other words, some initial starting conditions that we all agree upon, that this is how we're going to measure free energy changes to give us some understanding of the reaction relative to other reactions. Okay, so when we think about Fort Collins, Colorado, its elevation, we think about that in reference to sea level compared to, San Diego's elevation and its elevation relative to sea level. Okay, so but we have that reference point. Okay, so we need to understand that there's this reference point. Okay, and by that we mean starting reference point. Oops, sorry about that. I got to get rid of that. Maybe. There we go. Okay, so there's this reference point that we want to think about, right? And then we think about these numbers, okay? And when we think about this number here, negative 30.5, first of all, we think about this negative and we think, okay, well, that's going to tell us the direction that this particular reaction is going to go from its initial starting point, okay? And then the value, the magnitude, 30.5, tells us how far that's going to go, okay? Now, here's a really nice thing about the prime naught, or the standard free energy change. Okay, the standard free energy change is going to be essentially measured from a starting point of 1:1. Okay, there's lots of other things, but it's going to be a 1:1 product reactant ratio. Okay, and so what we'll often do is this. Okay, with the standard free energy change, or this free energy landscape, what we'll do is we'll say this, we're going to plot G, okay, and we're going to plot that versus a product reactant ratio. Or what we might call Q values. Okay, right, the product to reactant ratio. Okay, and we're going to put over here, essentially, if you think about it this way, our reactants in this case are ATP. We'll just leave water out of this, okay, but there's almost entirely ATP on this side, okay, and then there is going to be almost entirely ADP and inorganic phosphate on this side, our products. Okay, now to give us some landmark, I'm always going to put this 1:1 right here in the middle. That's right in the middle. We can say that our products are equal to our reactants. Now, that happens to be the starting place for our standard free energy change as well. Okay, and what we can say here then is this: because the standard free energy change for this ATP hydrolysis reaction is negative, we know that to reach equilibrium from our starting place, 1:1, it's going to have to produce products, meaning it's going to go towards the right. Okay, so we can very quickly from that description say that, okay, our equilibrium value is going to be to the right. It's going to be to the right of our starting point at standard conditions, which means it's going to be towards products, right? And so I'm going to go ahead and just pick a value over here. This is, right, I'm just kind of picking one. All right, you can actually do the math yourself, okay, and you'll come to a product reactant ratio of about 200,000 to 1 or something like that, okay? But nonetheless, we're going to put it over here, and we're going to call this our KEQ, okay, meaning this, that if we start here, okay, it's going to go in this direction to reach equilibrium based off of the negative 30.5, okay? Now, that's going to allow us to then draw this curve. okay, and we're going to say this, that our free energy is going to change in this way, okay? Let me go ahead and redraw that. It wasn't very good. These are kind of hard for me to draw for some reason. There we go. Okay, we'll go ahead and go with that, okay? Right, but what we have here is this landscape is showing how free energy will change as a function of our product reaction ratio. Okay, and you'll notice here that there's going to be this driving force for the reaction to dip down into, from an energetic standpoint, the point where we're at equilibrium. Okay, and we say that the equilibrium point is where the free energy has been minimized. Okay, right, and that's what you see here, that right here, our free energy has been minimized. Okay, now, we started under standard conditions somewhere around right here, and that means that the energy is going to dip down, just like if you're thinking about it as potential energy. A skier on the side of a hill is going to go down to the bottom of the hill. Gravity's going to pull him that way. In this case, it's not really gravity; it's an energy well, but it's pulling it that way. Okay. Now, let's move on and let's look at this, okay? Let's think about this, our actual free energy change. Once again, we can just think about it the same thing. We have a negative value, which means that under our starting condition, okay, we're going to go towards product to reach equilibrium, okay? And then we have to have some magnitude. Okay, how far we're going to go. Well, in this case, you'll notice that our magnitude, 52, is greater than 30.5, which means that we're starting further from equilibrium, okay, under our initial conditions and actual conditions than we would be under standard conditions. Okay, so I'm going to say, okay, well, I'm going to put them up here. Okay, my Q value, my starting point for my particular actual free energy change is going to be, okay, further to the left or further away from equilibrium than I was at standard conditions. Okay, so I have more potential energy as measured by the magnitude of this value here versus the magnitude here to go towards equilibrium, and the ATP can actually do more work within the cell because there's just more ATP relative to its breakdown products. Okay, and so again, this is going to go down into this energy well. Okay, sorry if you hear people in the background. I'm at home, right, as all of us are, okay, during this time right now. So if you hear people in the background, that's what's going on. Okay, all right. So that's what we've got here. Okay, that's how these free energy landscapes can be used. We can look at them and get an idea of, okay, energy, right? Energy is always going towards this minimum. Things are always dropping into a minimal energy standpoint, and that's where we would say that the system is at a greater stability, okay? And we call that minimum point the equilibrium point. And then the really only difference between standard free energy and actual free energy is where we're starting, okay? And we can use these negative or these positive values to determine, okay, which direction is the reaction going to go to reach equilibrium, okay? And then how far based off the magnitude. Okay. I believe that that's all that we need to say. Now, let's do this. Okay. And hopefully, maybe it's a good time for you to pause it and say, okay, well, what if I were to do this? I were to change this. I'm just going to flip that. Okay. Delta G prime naught, or our standard free energy is positive 30.5, and our actual free energy is positive 52 kilojoules per mole. This would be to make ATP, right? So in this case, we're just going to go in this direction. Okay, I'm just going to flip everything around. What would have been products had now become reactants, so I'm going to go ADP plus PI, and I'm going to go ATP over here. My products are what were my reactants prior to this are now my products. Okay, now hopefully you understand what's going to happen in the graph. The graph just goes completely opposite, right? What we have here is this, right? We'd look at this and we'd say, oh, it's a positive value, which means that my KEQ has to be over in this direction. right? I'm still going to start at the same place, the standard conditions. It's just that my KEQ is this direction because I'm making ACP now, and we're going to take energy to do this, okay? All right, and then, of course, same thing can be said here. The actual conditions is just going to be further up the hill, okay? So my free energy landscape, let me try and use a different color here, is going to be something like this. It would be essentially the reciprocal of what I had here before, okay, right? And again, oops, I wasn't very careful with this. Let me try that again. I'm going to go through our starting point. There we go. Okay, so again, we're going to start here at the same place. Right there is our starting point for standard conditions. This is we have to go in the opposite direction, okay? And to keep this reaction going, you have to actually add energy, okay? And we could put a new Q value, right? It would be somewhere up here, okay? All right, so this is always inherently tricky, this information, this stuff, okay? So if you have questions about this, by all means, go ahead and contact me. Hopefully this recording has helped you out a little bit, okay? All right, so I'm going to go ahead and stop, and hopefully you find these worksheets helpful throughout the semester.